Have you ever looked at a periodic table on a classroom wall and noticed that the elements near the bottom of the chart seem to exist in a different category from everything above them? Heavier, more unstable, named after planets and mythological forces rather than places or scientists. There's something about the way uranium sits at the end of that table that suggests it belongs to a different part of the story of matter entirely, not the part about building things, the part about what happens when things come apart. Most people have a feeling about uranium before they have a single fact about it. The feeling arrives first, assembled from decades of news coverage and film, and the particular vocabulary that surrounds nuclear anything. Dangerous. Glowing. Weapons. The reality of the element, what it actually is, how it was used for a century before anyone understood what made it remarkable, and why the property that makes it frightening is the same property that might help keep the lights on in a warming world, is considerably stranger and more interesting than the feeling. The world's known uranium deposits, spread across Canada, Kazakhstan, Australia, and Namibia, hold enough energy, if fully used in modern reactors, to power human civilization for centuries without burning a gram of fossil fuel. The element is more common in the Earth's crust than tin or silver. It is under your feet right now in quantities you would find surprising. And for most of the time humanity has known about it, we used it to make yellow glass. But here's the surprising truth. Uranium's story is not primarily a story about danger. It is a story about a property that sat completely undetected for over a century, hiding inside a metal that Victorian glassmakers were handling with their bare hands, until one afternoon in Paris in 1896, when a physicist left some photographic plates in a drawer and came back to find they had been exposed by something that wasn't light. Today, we're unpacking what uranium actually is, why its most important property was invisible to science for so long, and how a metal once prized for the color it gave to decorative glass became the most consequential element of the 20th century. To understand uranium's peculiar history, you have to begin not with physics, but with pottery. The element was first isolated in 1789 by a German chemist named Martin Klaproth, who extracted an unknown metallic oxide from a dark, heavy mineral called pitchblende and named it after the planet Uranus, discovered just 8 years earlier. Klaproth believed he had isolated a new element. He had not quite managed it. What he had actually produced was uranium dioxide, a compound, not the pure metal. The pure metal itself wasn't isolated until 1841, when the French chemist Eugène Melchior Péligot achieved the full separation. But neither discovery caused much excitement in the wider world, because uranium, as far as anyone could tell, was not especially useful. It was dense and difficult to work with. Its compounds produced a distinctive yellow-green color when added to glass or ceramic glazes, and that turned out to be its primary application for the better part of a century. Uranium glass, sometimes called Vaseline glass for its color and texture, was manufactured across Europe and America from the 1830s through to the mid-20th century. Decorative bowls, wine glasses, and tableware, all mildly radioactive, all sold without restriction, sat in the cabinets of ordinary households across the developed world. The people making and buying this glass had no idea that uranium had any property beyond its color. Neither did the scientists studying it. Think of it like a key that nobody realized was a key because the lock it opened hadn't been invented yet. For 100 years, chemists characterized uranium as they would any heavy metal, measuring its density, its melting point, its chemical reactions with acids and bases. All of those measurements were real and accurate. All of them missed the thing that actually mattered because the instruments needed to detect radioactivity did not exist, and the theoretical framework needed to understand nuclear structure was still decades away from being developed. The lock appeared in 1896, almost by accident. Henri Becquerel, a French physicist, was investigating whether certain minerals might absorb sunlight and re-emit it as the newly discovered X-rays. He planned to expose uranium salts to sunlight and then place them on wrapped photographic plates to see if they produced an image. A stretch of overcast weather in Paris interrupted his experiment. He put the uranium salts and the wrapped plates in a drawer together and waited for sunshine that didn't come. When he eventually developed the plates expecting to find nothing, he found a clear, sharp image. The uranium had exposed the plates in complete darkness, without any sunlight at all, emitting invisible radiation entirely on its own. Becquerel had stumbled onto radioactivity, and uranium was the element that revealed it. So if uranium was emitting energy spontaneously and continuously without any external input, where was that energy coming from? The answer, as is often the case in history, comes down to instability, at a scale too small for earlier science to have imagined. Uranium atoms contain 92 protons in their nuclei, which makes them among the largest and most structurally strained of all naturally occurring elements. That strain makes them unstable. Uranium nuclei shed energy over time by emitting particles and radiation, a process called radioactive decay, and they do so across timescales so vast that the uranium inside the Earth today is largely the same uranium that formed when the solar system coalesced roughly 4.5 billion years ago. Natural uranium exists in several forms called isotopes, atoms with the same number of protons but different numbers of neutrons in the nucleus. The overwhelming majority of natural uranium, over 99%, is a form called uranium-238, which decays so slowly it poses minimal immediate hazard. A much smaller fraction, less than 1% of all natural uranium, is a different isotope called uranium-235. This is the form that changed the world. When a neutron strikes a uranium-235 nucleus, the nucleus doesn't just decay slowly, it splits. That splitting, called fission, releases energy and additional neutrons, which can strike further nuclei, causing them to split in turn. Under the right conditions, this chain reaction is self-sustaining and releases energy on a scale that has no equivalent in conventional chemistry. A single kilogram of uranium-235, fully fissioned, releases energy equivalent to burning roughly 3,000 tons of coal. The physics was understood theoretically by the late 1930s. The practical consequences followed within a decade and reshaped the world in ways that the Victorian glassmakers handling their yellow bowls could not have begun to anticipate. So, the next time you encounter uranium in a news report or a conversation, bracketed by the familiar vocabulary of risk and weaponry, you'll know the longer story. An element discovered in a German laboratory in 1789, spent a century coloring decorative glass, accidentally revealed the existence of radioactivity to a physicist with cloudy weather and a drawer full of photographic plates, and then turned out to contain, in its rarest isotope, the most concentrated energy source that naturally occurs on the surface of the Earth. The danger and the promise come from the same place. A nucleus so large it cannot hold itself together, slowly, unstoppably, falling apart.